Hello, and welcome back to Stats Probability Notes. We're moving on to Chapter 4, so hopefully you have your CAMI. And we're starting with some notes here. So talking about how many children are in your family. We're going to count up the number of children in your family, including yourself, including all your stepbrothers, etc. So let's say that there's 20 kids in the class. And so we each get to reply and say if there's one child in the family, so that's usually like an only child, or if there's two, so like me, I have one brother, so I would fall under the two, or if you have two siblings for a total of 3 kids, et cetera there. So I collected some data, aka I made up some data, and we have 3 out of 20 kids in class are only children. We got 5 out of 20 have one sibling. I got 7 out of 20 have 2 siblings for a total of 3 kids. 3 out of 20 have 4 kids in their family total, including themselves. And then 1 out of 20 have 5, and 1 out of 20 have 6 or more. So, is this a valid probability model? So 2 things we have to check for this is, first, are all of the probabilities between 0 and 1. And right now they're fractions, but we don't have like 25 out of 20 or anything like that right now. So yeah, all of our probabilities are between 0 and 1. And second, do all the probabilities add up to exactly 1? And they should. So when we have 3 out of 20, and we add that to 5 out of 20, that's 8 total. And then 7 more is 15, 3 more is 18, 1 more is 19, and 1 more is 20 out of 20. So yeah, all the probabilities are between 0 and 1, and yes, they all add up to 1 when we do that. So we do have a valid probability model. Our distribution here is valid. The next question is 5.7167 a possible value for x? So x is the number of children. Can you have 5.7167 children in your family? No, you cannot have a decimal or fraction number of children in your family. So this is a discrete distribution here. This is discrete because there's gaps. So we can't have that in between 1 and 2, 2 and 3, but there are gaps in our data. There's little jumps. So if we were graphing this, graphing these as points, there would be 1 kid, 2 kids, 3 kids, and so on. But so we don't have a continuous line connecting. There's nothing connecting between 1 kid and 2 kids. All those decimals, all those fractions in between. So we're going to make a histogram to display the information with x on the horizontal axis and then this probability on the vertical axis. So we're going to head over to Stapplet.com, and I'll show you what to do when we get there. So on Stapplet.com, I went and chose discrete random variables. And so on discrete random variables, it asked for a variable name, and I typed in the number of children, and then put in my data here. And so I had it as fractions initially. So I just did 3 divided by 20, and 5 divided by 20, 7 divided by 20, etc., to get all my probabilities for each number of children. And then hit begin analysis, and it gave me a histogram where I got the number of children, and then the probability of that occurring. And it even gave me a mean and standard deviation as well in the summary statistics. So you can go to Stapplet.com and create your own discrete random variable histogram using the data we created and copy paste that into your notes. So it does ask us to describe its shape. We're trying to see if it's normal, where it goes, up and then comes back down, and it's symmetric on both sides, so normal distribution or symmetric, or if our data is skewed one way or the other. And we can say this is kind of decently symmetrical, but it looks like there's more data on the left. So probably the best response for this graph would be skewed to the right, where that data is over on, there's all that extra data, but it's not a lot to the right, pulling it over there. If we had more data points kind of stretching it out to the right here, if we had a 7, 8, 9, then it would be pulled even further to the right and be more skewed. But skewed, maybe kind of symmetrical, and we'll kind of see exactly what our values are showing us as well. So number 4 says describe in words what probability of x is greater than or equal to 3 means, and then we want to actually find it. So the probability that x is greater than 3, remember x refers to the number of children in the family, so that means the probability of greater than or equal to 3 siblings, 3 children in the family. So to find that is greater than or equal to 3. Sorry, don't have the greater than or equal to sign when typing it out, but you can always get it when you're doing the equation editor there. Is going to be the probability that x equals 3 plus the probability that x equals 4 plus the probability that x equals 5 plus that last probability that x is 6 or more. Let me make that so we can see it real quick. So the probability that x is greater than or equal to 3 is going to be that too far. Is going to be that 3 out of 20, or the 7 out of 20 plus the 3 out of 20. So we got the 7 out of 20 plus 4 siblings would be 3 out of 20, 5 siblings, 1 out of 20, 6 or more is 1 out of 20. So we have all the same base of our fraction, 20, 20, 20, 20. So we add 7 plus 3 plus 1 plus 1, and that gives us a total of 12 out of 20, and we can change that to a decimal if we wanted. What's the difference between 4 and 5? In 4, we had this greater than or equal to, and in 5, we just have a greater than. So we just want the probability of greater than 3 children in a family. And basically the same formula, except we're not including that x equals 3. So without that, we have the 3 out of 20, the 1 out of 20, 1 out of 20. So I'm just looking at that right there. And we'll add 3, 1, and 2, and that'll give us 5 out of 20, which seems like 25%. Next, we want to find the average number of children in the families of students in this class. And so, what we're used to doing is just taking these numbers and adding them together and dividing by the total amount there are. But since we have the probabilities of how many there are, we're going to kind of use that as well. So we have that there is, for one child in the family, there's 3 out of 20. That'll tell us how many children there are there out of the 20. And then for when we have 2 children in the family, we have that probability 5 out of 20. And so we're just going to do this for each of the values. We're going to take that x value, 3, multiply it by the probability, 7 out of 20. Same with 4, 3 out of 20. Same with the 5, 1 out of 20. And this is where it gets a little tricky. We're just going to assume that that 6 is 6 out of 6. We're not going to say it's any more. We're just going to say it's 6. And then so we would add all that up and determine that the average value of the x value is, when we multiply and add all these together, we get that the average number of children, drop my thing there, is 2.85. And that should and does match what our wonderful Staplet.com gave us there as the mean, 2.85. So that's how they calculate the average of the values. So does that value, does the average of these x values tell us the number of children in the family of students in this class? And yes, it does. That average does tell that. So what that means is that on average, in this made-up class, there are 2.85 children per family. So something I just want to mention here, we got to be careful with our boundary values. If we're including a value or not, then that changes it a lot, from 12 out of 20, which is over 50%, down to 5 out of 20, which is just 25%. And I also do want to talk about this discrete. So we can't have the values in between 1 and 2, in between 2 and 3. Another example that would have those values could be something like, if we suppose that y represents the time in minutes a randomly selected high school student runs a mile, then could 5.1767 be a possible value? It sure could, because that would be 5 minutes and some extra time. I think I have this written backwards, 7167. So yes, this would be approximately 5 minutes and 43 seconds. So that makes sense. That can be changed into an actual time that makes sense. And that would be a continuous variable versus our discrete variable, where there's no gaps in our data. So we can call this a continuous variable. Where we can have anything from 5 minutes up to 6 minutes and all the time in between. All right, let's wrap this up with the important ideas from this section, including those vocab words, that discrete and continuous. Let's start with, on the left side here, we're going to have 3 columns, and we're going to say if we have a valid probability distribution. And we saw this in one of the first questions there, that all the probabilities are between 0 and 1. And we also need to, when we add the probabilities, the sum of our probabilities adds up to 1. So that's our first one. And then our second, kind of building off of probability stuff we did last time, the probability that X is greater than, I'm going to draw in an equal to here because I don't have my symbol ability to do that. So probability that X is greater than or equal to 3 is different from the probability that X is just greater than 3. So when we include that is equal to, we're including that boundary and kind of changing that value there. And then finally, we can say that we have discrete variables, which is a fixed set of values with gaps. For example, your number of siblings. And we have continuous variables, which has all possible values with no gaps. For example, your height, weight, time, and there's plenty of other examples as well. So make sure you have all those notes. You'll work in class on the check for understanding here about Indiana University in Bloomington. Go Hoosiers. And answer these questions. So let your teacher know if you have any questions as we get back into notes over probability. See you soon.